Okay, let's start. So yesterday we introduced some basic mechanics of the AFM technology, and today we will continue and introduce the widely used imaging mode called PeakForce QNM. So before that, we will finish yesterday's introduction of the force curve. So basically, we would like to use AFM to measure the modulus of the sample. And the modulus is used to characterization the material's mechanical properties. So our basic idea is we're starting with the Hooke's law. We're starting with Hooke's law, which is the force is proportional to the deformation. And the coefficient, we gave it a name, it's stiffness. But the stiffness is it includes both shape and the materials contribution. So for material, we would change it to this formation, and the sigma is the stress, and the epsilon is the strain. When we consider the direction, the sigma and the epsilon, they should be tensor. And the modulus itself, of course, it should be a tensor. And for isotropic material, we can reduce this modulus tensor just to only two components. And one is the modulus number, and the nu, we call it the Poisson's ratio. It used to describe the relationship between the direction along the force and the direction perpendicular to the force. So that's the isotropic materials, and usually when we do the material study, especially for those polymers, biological materials, they are isotropic. But of course, if you are doing crystallized structure, salt, sugar, or some other stuff, we need to consider the directions. We need to use group theory to help us reduce the numbers, the components of the tensor. And for this one, this is just one description, as we said, because this is just we can use the concept in the algebra. This is just a linearized space, and for this isotropic materials, it only requires two bases. We can use modulus and the Poisson ratio. We can also use the shear modulus and the bulk modulus to describe it. Especially for this shear modulus, this is widely used in the biological materials. And so usually when we do some measurement for cells and the gels, they would use shear modulus. Okay, and for the modulus we used in this description, this is for compression. And for the compression, we would give it a name, it's Young's modulus. So our study is we try to get the Young's modulus of our sample. And to measure the Young's modulus, usually we would use a machine. We would make a defined shape device using our materials to fabricate this device or sample, and then we put it on a plate and use a stylus to press it. And this stylus, we can record the force, and of course we can use a camera here to monitor its height change. Of course, usually nowadays there are many kind of this kind of instrument. You can use camera to record, or you can use a position sensor. on this stylus, and it records the displacement. And if you are using a position sensor, it's almost the same as that nano indenter. Nano indenter is this kind of principle. There is a force transducer. I'm sorry. There is a force transducer, or there is a force stylus, and they can monitor its force. And there is a position sensor inside the stylus. So it's the principle of that nano indenter. Okay, and no matter how, this kind of machine is to press on the sample, and as such, we can record the height change against the force we applied. And as we know the original height, we know the section, we know the area of the cross section, so we can change this curve into the height change, delta height divided by the L0. And this one is the force divided by area, which is stress and strain. And then this curve will transfer this. And so the slope of this curve should be our Young's modulus of our sample. That's how we measure it using the macro scale material, using the macroscope instrument. And for our AFM, the story is different, because we use AFM to measure the property at the nanometer scale. So we cannot define our material, we cannot define our samples in such shape. It's a random shape. So for this kind of sample, the height, original height is unknown. The section is also, the cross section, the area of cross section is also unknown. So we cannot directly to capture this kind of stress strain curve. Instead, we have to capture a force against the distance, curve. Okay, for AFM, we are using a probe, and the transducer or the force sensor we are using is a beam, which name is cantilever. So we actually use the deflection of this cantilever to measure the force. And so to measure the deflection of the cantilever, we have to use a laser. And we're using the reflection of the laser to measure the deflection of the cantilever. So finally, we are actually measuring the reflection of the laser to characterize the force. So we are measure vertical against distance of the for our AFM setup. So we will capture a force curve. In a typical force curve, we will say this slap in, which is due to the attraction force between tip and the sample. And this is a quantum chemistry concept. And usually we would define this point as a contact point. And after that, we think the sample has been compressed. It has a deformation. And we would apply to reach our maximum force. And after that, the probe will retract. Usually there is an adhesion force between the tip and the sample. And the adhesion force includes two parts. One is tip-sample interaction, and another thing is the capillary force, which is due to the surface tension. So this one, we call it adhesion force. So it has two parts. One is tip-sample interaction, another is surface tension. And we don't want surface tension. So we have two methods to get rid of surface tension. One is super dry. One is completely fluid. And the completely dry is actually very hard to obtain. So usually when we want to measure the tip sample interaction, we need to use fluid environment. And this tip sample interaction is widely used in the chemistry and biology. For the chemistry, usually people use it to measure the interaction between different chemical bonds. For example, gold and thiol, and we have some hydrogen bonds. For example, amine and carboxylic acid. And for biology, it has wide application. For example, you have some ligand and it has its receptor. For example, you have the antigen, you have antibody. You all can use this kind of technology to measure the interaction force at the molecular scale. So that's the interaction. But for those, we need to remember, we need to get rid of the surface tension. And then that's our finally we capture a force curve. Of course, there are some noise. That's the final force curve we get. And then for this sample, we need to echo back. We want to get the stiffness. So our equation we write it down here is the force equals to the stiffness times the deformation. And so we need some change. We are actually monitor the vertical against the distance. So we need to do some change. The first is the force on sample. We use the Newton's law to change it to force on tip. That's Newton's law. And then the force on tip, we change it to the deflection of the cantilever. And the deflection of the cantilever is monitored by the laser beam, which is captured by vertical value and the lateral value. So our task here is to finish this roadmap. We actually monitor vertical. We want force on sample. So we need to calibrate this one and this one. And from vertical to deflection, we are actually use this AFM technique. They call it deflection sensitivity. And to capture that, we do this force curve on a super hard materials. Usually it is sci-fi. But we need it to be a clean sci-fi. The next, once we get the deflection, we need to change it to force on tip. And this one is actually the stiffness of our cantilever. And usually in AFM community, they call it spring constant, which is Kc. So it's actually the same thing. And after this steps calibration, we can get the force on samples. And another side is the deformation. In the AFM, we are capturing the travel distance of the scanner, which is a piezo, you will all know. So this scanner movement is contributed into deflection and deformation. So once we capture the deflection sensitivity, we can write it down as this one. So after the calibration of different sensitivity, we can get the deformation of our sample. So basically, we calibrate, we calibrate different sensitivity, we calibrate the spring constant, we can transfer this force curve into the force against the deformation curve. And finally, we get our stiffness. And this is our phase 1 job. The next job is we try to seek the Holy Grail. Okay, so yesterday we introduced this AFM technology, and we stop at the we stop at the spring constant calibration. So today we will continue. So for the spring constant, Kc or Hc is the same thing. Kc calibration. We have several methods. We have the first method is we use our theory. We have the geometry of our cantilever, and using the geometry and the modulus of our cantilever, we can capture the stiffness of the cantilever. That's we are using the theory to do this. And the second, we have some quite super expensive way to do it, is we are using a known stiffness beam to do this calibration. And actually, we are just do a force curve on this reference cantilever or reference beam, and to get the modulus, or to get the stiffness of our cantilever. And the third one is the so-called Cleveland way. The Cleveland way is based on the resonance frequency. The resonance frequency of our cantilever can be written down as in such a simple model. And if we add another mass onto the cantilever, we can actually get before adding mass and after adding masses resonance frequencies. And we measure two frequencies, we can get Kc and the original mass out. That's quite widely used for the colloidal AFM probes. For those researchers, they will glue a sphere onto the AFM probes. They usually will use Cleveland method. And the fourth one, we call it the thermaloid or thermal tune. The theory of this one is, we said the cantilever, when we put it in the atmosphere, the cantilever will start vibrate due to the Brownian motion of the air. So the vibration energy will equals to the thermal energy of the environment. And so for the vibration energy, we would, I just need to write it up. So the fourth one is the thermaloid. So it's the vibration energy is equals to the thermal energy. So the vibration energy is we just using the work done by the Hooke's law force. So this one is actually Kc times Z squared. And the right-hand side is the thermal energy. The thermal energy we're using thermodynamic theory. It is kBT. Okay, so and then the Kb, the Boltzmann constant is known. The temperature we can easily measure, and then the Kc just equals to the kBt, and the Z here means the deflection. Right, our beam is vibrate. Actually means its deflection is oscillate, and then this Z, this deflection can be written down as the deflection sensitivity times the vertical change. So to get this one done, we actually need to monitor the vertical under this temperature. So we monitor the vertical change against the time. We would observe this kind of curve. And from this curve, we calibrate or we calculate its amplitude. Then we can get the vertical out. We can get the vertical out. So that's the main idea. Of course, in the instrument, usually they will do a little bit change. Once we calibrate this time domain information, they will do a Fourier transformation into the frequency curve, frequency domain, and usually you will see this kind of curve. But that's just the mathematical game. So way from this vertical against the time curve, we can capture this vertical value, which is the amplitude. We capture the vertical value if we have calibrated the deflection sensitivity, and then the Kc is no. That's the main idea behind. Okay, so that's the fourth way, which is the widely used one, the thermaloids. But for this method, we require to monitor the vertical change. If our probe, the Kc is large, if our Kc is quite large, this curve will be, the signal of this curve will be quite small. For such weak signal, it's hard for us to obtain its amplitude, and then the sensitivity will significantly reduced. So usually this thermal tube method is for Kc quite small. Usually it's smaller than 1 Newton per meter or 10 Newton per meter. But usually it's this kind of softer probes. And there's another way can be used to calibrate the spring constant, and it is developed nearly 2,000 years. It is developed by this Professor Sader. And he is using the hydrodynamic theory to do this calibration. He considered our cantilever. Is a kind of beam, and this beam is beating it's beating the air inside the environment inside its surroundings. So it will sense some you can say friction or hydrodynamic force, and due to the environment outside. So basically, this kind of theory is we can write the Newton equation down. So the force sensed by our cantilever equals to first, of course, we have the Hooke's law. So it's negative Kc times J is deflection. And since it's moving in the environment, it will sense a hydrodynamic force. A hydrodynamic force, usually we can write it down as the viscosity times its speed. And we'll use the Newton's law equals to its mass times its acceleration. And then our task now is to solve this this equation. So we'll write it down in this way: plus eta divided by m dz dt plus kc divided by m z equals to 0. Okay, to solve this equation, I think it's you have done it many times in your university. So for this kind of equation, you have the second order derivative, and it's zero and itself. So we will use we can guess its solution should be an exponential function, and we can write it down in this way. It has an amplitude, it has an exponential function. So I write it down as this form. So my task now is to get the value of alpha and amplitude. Okay, so how to do it? Just put it back into the equation. So we take second order derivative, so this alpha comes out. And I do first order, so it came out one time. And there is eta divided by m and E alpha t, and plus Kc divided by m. Kc divided by m, I can write down as the resonance frequency. Okay, so I write it down as resonance frequency as well. And it's A E alpha t equals to 0. Of course, from this equation, we can tell the A equals to 0. It should be the solution. But A equals to 0 means the cantilever is constantly static. Usually it's meaningless to us. It tells us no information of the case. So the A equals to 0, we just accept it's a solution, but that's not the solution we want. So the second, when A is not 0, when A is not 0, so you can divide it by A on both sides, right? Because A is not 0. So if A is not 0, we can get the alpha E alpha t plus eta over m alpha E alpha t plus omega 0 square E alpha t equals to 0. Of course, E exponential function is not 0, so we can divide it by it on both sides. So finally, our game is alpha square plus eta om alpha plus omega 0 equals to 0. Okay, so I can put it here. So for this one, we know it in high school. The alpha equals to 2 over negative eta over m plus minus root square of eta over m square minus 4 omega 0 square, right? So we need to do some discussion. So first, if eta over m minus 4 omega 0, this is larger than 0. And this means the eta is large. The eta in our equation means viscosity. So means viscosity means we are facing a large hydrodynamic force. So this kind of large hydrodynamic force in your physics, in your mechanics, it means you are facing a large damp. And for this kind of solution, we can write it down. The alpha is quite simple. Is 2m eta and plus minus 2m squared minus omega 0. Okay, and then our equation out is times plus minus we are get this kind of curve, right? We are get this kind of curve. Okay, the second is the same. If we have the eta over m minus 4 omega 0 square equals to 0, and we know it's the critical damp. It's the same results as this one, okay? And the last one we want to discuss. So I just write this down. It's larger 0. The J is the A, E times okay? And if it's critical, this is equals to 0, means the J is A, E, eta. Okay? The third condition is if the eta over m eta over m square minus 4 omega 0 square less than 0, means inside the square root form it is a negative value. If it's a negative value, you take a square root of it. It's an imaginary number, right? So I can write it down in this way. The alpha equals to 2m eta plus minus I, the imaginary number, root square of negative 1 times okay? So finally, my solution is J equals to A times E I omega 0 square minus eta over 2m square t. Okay, for this kind of exponential function, we can tell using the Euler's equation. EI theta equals to cosine theta plus I sine theta. We have the Euler equation. And so we can tell this one is actually a what? An oscillation. So our results, so our curve of this one should be something like that. Let me write down there. This is the deflection over time, or Z over time. Right? It's an oscillation, but its amplitude is reducing against the time. This one will follow eta over 2mt, right? And its oscillation period is decided by omega 0 minus eta over 2mt, eta over 2m squared. Right, that's our final result here. That's our final result here. So as such, we will define a factor here, and this factor is the famous, we call the eta over m. We call it we write down in this way. Since eta over m is at a unit of frequency, so we just give it a name, it's omega 0 over q, and the q here is the quality factor. It is used to describe the relationship between the resonance frequency and your hydrodynamic force. If the Q is large, means your hydrodynamic force or the eta or the viscosity is quite low. If the Q is small, means you are facing a large hydrodynamic force. That's our idea. Okay, so finally we get our solution. So and as such, we can try to get our Kc out from this method. So we have a probe. We have our cantilever. And we put our cantilever inside the environment. It will sense a hydrodynamic force. And this hydrodynamic force can be characterized using our quality factor, using our resonance frequency, and our key idea is to get the eta. So this eta is the hydrodynamic force contribution. So for the eta, we can use the hydrodynamic method to try to calculate it. For that, we need to know the viscosity of our environment. We need to know the density of our environment. I am sorry, I forgot the name. That's the Rayleigh number we used to capture it before. So we calculate out the hydrodynamic force. Actually, we get eta out, and then if we can measure the quality factor of our cantilever, and then the omega 0 is out. The omega 0 we know is Kc over m. So finally, our Kc is inside the omega 0. So the key idea of the Saders method, he is using a hydrodynamic model to try to calculate the hydrodynamic force. And then if we can measure the quality factor and the resonance frequency, we can get the spring constant out. That's his whole idea. So our AFM job now is to measure the resonance frequency and the quality factor. How is we doing the same work here? We are using our AFM to monitor the vertical change against the time. We will get this kind of damped oscillation curve. From this damped oscillation curve, we can do a Fourier transformation, change it into a frequency domain, and we will observe a curve, something curve like this. And with this curve, we get the frequency and the quality out. This step is done by thermal tune. But at this time, from the thermal tune curve, we don't need to measure the amplitude anymore. We just need the frequency and the quality factor. So even for some hard probes, even for some hard probes, although we cannot get the amplitude, but we can still get the frequency and the quality factor. And from the resonance frequency and the quality factor, we can get the spring constant out. And sorry. This third method, the Professor Said has developed his method around 2000 years. And I think in 2010 or sometime, he developed his own applications. And this application is on iOS only. And you can search for it. Its name is Said method. And once you enter this application, and you can write down your resonance frequency and the quality factor you measured using the thermal tune, and then you type in the geometry into this application, and then you can get, and this application will give out the spring constant. For example, I write down the length is 120, and the weight is about 35, and the resonance frequency I say 300, and the quality factor I gave it 500, and I did calculate. It gives me a spring constant, and then you can type in your in the AFM softwares. But that's the old ways, and of course you can reach Professor Said's website is on this one, and you can search. I'm sorry, this is his this is his website, and visit his website. You can type in your resonance frequency and the quality factor. It gives out the spring constant. But nowadays, Dr. Said want to expand his method, so he has established an online library, and he invited many AFM researchers to do this kind of stuff, and as such, he made up a library of his Said constant, which means if you have a defined geometry, this defined geometry is helped to calculate the hydrodynamic force. And you type in the geometry of your cantilever, you type in the environment, like this Reynolds number, the viscosity, the density of your solution. And then you have a defined geometries. And then from this, he can calculate a Said constant. And so his idea is our Kc is proportional to some Said constant. And then you type in your resonance frequency and the quality factor. He can give out the spring constant directly without you typing the geometry again on his website or his application. So nowadays, this Said constant has been established, and Brucker also do some collaboration with Professor Said, but Brucker is, it's capitalized. They just want to sell his own probes. So Brucker provide Said constant for his own probes, which is TESPA 150, TESPA 300, TESPA 525, and Scan Assist L Super Sharp. And I remember there's another one, RFESPA40. And there are so many other probes, but Brooker did not give the seed constant in his software. So that's the game of that's the game of Brooker. So, and if you are using the probes of these 5, you can find the seed constant in the softwares. We can show you this afternoon. But if you are using other probes, I'm sorry, Brooker we have to go back to our applications. But if you search online, the Professor Said has established his library widely, not just Brooker's probe. Okay, so if you are using other probes besides this 5, you can go back to the application. Or if you know the probe you are using has the same geometry of this 5, you can just use this 5 instead. You can choose this 5 instead in the software. Let's try to cheat Brooker's software. Okay, so that's about this stuff. That's about the SAID method calibration. I would say SAID method is I think it's the first choice calibration method of the spring constant. It is more widely used than the thermal tune, because SAID method is really quite helpful. Okay, so that's about the calibration of our spring constant. So yeah, you can have the application on your cell phone. Okay, so that's the old method you can use to calibrate your probes. Besides that, of course, you can use the power of money. Let's look back why we need the SAID method. Besides the SAID method, we have the thermaloid. The thermaloid is based on spring constant equals to the deflection. I write it down, deflection square and KBT. The K idea is this. So we need to measure the deflection. But on AFM, we have to use the vertical to measure it. If our probe is hard, the vertical signal will be quite small, will be quite weak. So it's hard to measure the vertical values. But this is not the only way to measure the deflection. We have many other stuff. So nowadays in the industry, they use other machines to measure the deflection change. And you get the deflection change, then you can get the KC out. Some guys, they can use Doppler's effect to measure the deflection change. And this method has been widely used in industry to measure the deflection. So the probe factory, the probe manufacturers, before they shipping to you, they use Doppler effect instruments to measure the deflection and get the KC out and write down the KC number. And then he sell the probe to you in higher price. So that's so this kind of strategy has been widely used. Brooker has this kind of probes, and Lalo Ward has this kind of probes. You can just, if you think your time is more precious, yeah, you can use the power of money to do this, and invite and ask them for help to get the accurate KC. The principle besides is the same. You are using thermaloids. They are using other instruments to get the spring constant out. Okay, so I think on on Friday, we will use this kind of probes. They have a QR code to scan it and to get the spring constant out. It's quite sweet because we just jump all this calibration stuff. Okay, so we make a small theory. We make a small summary. Yeah, all this stuff, all this method is established maybe 15 years ago. I think it's in 2010, around 2010. Broker application scientists, they published lots of this kind of papers to discuss the calibration stuff. And they even made up this kind of summary to tell you the uncertainty, tell you the uncertainty of each steps. Yeah, they did very good jobs. Yeah, and so they can estimate for each method, the uncertainty of each method. And from this table, we can get out that the SAID method is pretty good. Yeah, the SAID method is pretty good. And so that's why it's widely used nowadays. And the reference cantilever is also okay, but this one is too expensive. Nobody uses it anymore. And the ADMAS is okay, but it's just a limited application, only for colloidal probes. And for the using the geometry to calculate directly is quite, it has large error. Okay, so basically that's the Brook summary. So we recommend you using the SAID method for your first choice. And then we can have the thermotune. And the thermotune is just for soft probes. And the SAID method in the previous discussion, the SAID method is only for diving board probes, and is not suitable for this kind of V-shaped probes. But nowadays, Professor Sader, he changed his method, and it can also be used for this kind of V-shaped the cantilevers. So yeah, but in the traditional in the traditional report, it is the diving board one. Okay, so that's the spring constant calibration. So we make so after we finish this step, we finish our roadmap. We need the stiffness. We need the stiffness. We need to get the force on sample out. And the force on sample, we give it again, is force on tip. Force on tip, we use the spring constant, the deflection. The deflection, we use the deflection sensitivity. That's the vertical value. And the deformation, it equals to the Z. I'm sorry, the Z here means the Z displacement of our scanner minus the deflection. And of course, it equals to Z minus deflection sensitivity times vertical. So we can play the games. Like this. We have our original force curve. I'm sorry, we have our original force curves. And the original force curve is vertical over Z. And I use the blue pen tool for the approach. It's something like this. And then we need to make some change. So the first, for the first step, so for the jump this one. So for the first step, we need to change the x-axis. We need to change it to the deformation. So we need to use the z minus deformation, deflection. And the deflection equals to a deflection sensitivity times vertical. But remember, we need to do, before that, we need to do one thing. Our vertical value, it has a baseline. The baseline is something like this. And on the baseline, we think the probe does not sense any force. So we need to subtract the baseline. And after the baseline subtraction, this baseline value should be 0. The first step, we call it baseline correction. Of course, this is done by software, but usually it requires you to tell the software which one is baseline. Okay. After that, we can easily to apply the deflection sensitivity, and you apply deflection sensitivity. So the y-axis is now deflection sensitivity times vertical, so it can go to deflection. And for the x-axis, you can do the z minus deflection, which is deformation. So you get a curve. Since you are doing the x-axis minus a positive value, so the curve will be has a smaller, it will have a larger slope compared to this one, right? So that's this diagram want to say. This one is more slope than this one. Okay, so after that, you can apply the spring constant. So the y-axis could be changed to force. And then this one is z minus deflection. And so our final curve will be something like this. And after that, the z minus deflection, we cannot change it to deformation because it requires us to tell him the 0 point, and which means from which this z minus deflection means you are compressed the sample. So we need to tell the software this one is our contact point. So after that, this is the 0 point of the deformation. So our curve after that will be deformation. And the deformation is something like that. This one is 0. So finally, this is our curve, the force against the deformation. And then from the slope, this is our stiffness. That's the scientific way to process this force curve. But the broker did some stupid things again. So the broker, I'm sorry, the broker thought our users may not be able to understand this step. So they make a transformation of this curve, they sweep this curve into this kind of the formation. And in this kind of formation, the x-axis now, Brooke gave it a name, separation. Gave it a name of separation. And now the scientific information is I think it's kind of loose in Brooks expression. And now we can tell from this curve, if you make a sweep, it will change to this kind. So it's force. And Brooks said it's separation. And now the curve goes to something like this. And again, we can still find out that the contact point is somewhere here. And the separation value on the contact point is the maximum deformation, right? That's the maximum deformation. So it's kind of stupid thing. I'm sorry. It's hard to understand. This kind of expression is straightforward. So if you search back the reference maybe 10 years ago, in the scientists they process the first curve, they will stop here. They will stop here. You define the 0 point of the deformation. That's it, and then you can get the stiffness out. But Broca did some stupid thing. He changed it into this form. So in your Broca software, you finally capture a curve, something like this. And then, of course, the slope of this curve is not the stiffness, right? You should add a negative number here. So that's Brooke did. So usually when you search for papers in the scientific papers, the final curve is something like that. Even on the non-indented, your final curve is like this, not like this one, not like this one. Okay, so if you want to publish the paper and the reviewer asks you for typical force curves, yeah, please change it back to this. Okay. Or of course, nowadays the Brooks icon is the main AFMs. Some reviewers would accept this kind of curve, but yeah, for me it's kind of stupid. Okay, so after this, we finally get our first curve down. We calibrate difference sensitivity, we calibrate spring constant, we get our first curve. And the first curve is force against the deformation, and the slope is the stiffness. And then from the stiffness, we finish our phase 1 draw. Okay? Okay, let's take 10 minutes break, and then we go back to the next step. Okay, we finish the stiffness, and then we can go to our next step. Is finally we want to capture the modulus. So it's the same. We have the vertical, we have the Z, we calibrate the difference sensitivity, we calibrate the spring constant, and finally we get the force, we get the deformation. And then from this, we can have the stiffness. And the stiffness, as we said, is not our holy grail. We still want the modulus out. So from the stiffness to modulus, we need to use the power of theory. And this theory is established in 19th century. Sorry, we are using some classic theories. So this theory, they call it contact mechanics, and this the main theory established by our famous Hertz. And Hertz established this contact mechanics, and his basic idea is quite simple. So we have two spheres. We have two spheres. These two spheres, they are uniform. So that means it has a defined radius. It has a defined modulus. His key idea is we compress these two spheres together. What the stiffness looks like. That's his total idea. So in our life, in our daily experience, for example, you have two bottles and you just compress the bottle. You can sense how stiff it is. But if you squeeze them together, we can sense these two bottles together. It seems like it is stiffer as you compress them together. The key reason Hertz think about it is that it makes the same materials, so its modulus should be the same. So Hertz think about it in this way. I have one sphere, two spheres, I'm sorry. I write down in the, I draw down in, I have two spheres. At the beginning, there is no force between each other. So the contact point is just one point. And then when you use force to squeeze them, and then it is our classic compression experiment. And Hertz would define the deformation will be equals to the 2r minus the distance of center, right? As you squeeze, the distance of the centers will reduce and it will cause a deformation. That's Hertz defined. And then I can use a force to squeeze them. So Hertz would get the stiffness of these two spheres together equals to the force divided by the deformation. And his series tells it's how to describe our experience. We compress the two bottles, we compress these two spheres, we sense it's harder and harder and harder. And the reason is that Hertz think that once you compress these two balls, the contact point is increasing from one point to a face. And this face should be a circle, right? This face should be a circle. So as your deformation increase, this cross-section area is larger and larger and larger. And once it's increased, you will have more contact area. And as the contact area increase, the interaction between each other is increasing. So it becomes harder and harder and harder to compress the two spheres. That's Hertz's idea. So his idea is the stiffness will increase. And as such, it is a function of our deformation. It is a function of our deformation. So he defined at these two spheres. So these two spheres, he defined a parameter here. It's the radius of the contact area. He called it AC. He called it AC. That's the radius of the contact area. And finally, his equation is the stiffness equals to 2AC times the modulus. So with this theory, we can solve our problem quite easily. So now this field is our probe. This field is our sample. So the probe apply force on this sample. So we are actually compress our sample. We are actually compress the probe and the sample together. So the stiffness we get, the stiffness here we get is this totally. So we can use the Hertz model. If we can calculate the contact radius, we get the modulus of the system together. Of course, this calculation requires the stiffness is the total stiffness, and the modulus here is the total modulus here, because we are combining these two things. So we need the serial connection. The total K, the total stiffness should be tips stiffness plus samples stiffness. Or you can write in another way. The total modulus equals to the modulus of the tip plus the modulus of the sample. And from this step, the modulus of the tip is known because we are using the silicon probes. So this one is a large value. The modulus of the AFM, the modulus of the silicon is 165 gigapascals. So the probe is quite hard, so we can get rid of this one. So the modulus we get, we think equals to the modulus of the sample. That's our theory. Okay, so this modulus in the, if you check our manual, they will call it reduced modulus. Or it's a total modulus of the serial connection of tip and the sample. Okay, that's Hertz theory. And the Hertz theory, we get the result quite quickly, but hey, it took him several pages to do this calculus. So I jumped, oh, sorry. No, it's not this. Let me see. Okay, I jumped this part and I would share the Hertz original paper. Of course, it's not paper. Nowadays, his theory is right down in textbooks, and we can share the textbooks with these slides. And if you really want to some reference about this theory, you can quote those textbooks. Okay, there's no so-called papers about that because that's too classic. So usually we will quote some textbooks for this step. Okay. So after that, the job is quite easy. The job is quite easy. So the history is he established his model. It's quite simple. It's just the stiffness equals to 2AC times modulus. And then in the 20th century, those people made some change because they need to introduce quantum mechanics here to make some modifications. But for their job is just to try to do some work on this force, because in Hertz in Hertz model, he only considered this force, but at the nanometer scale, this force we need to think about the quantum chemistry. So in the 20th century, you can say those guys made some changes, and they're starting from this guy Bradley. His job is introduce the Lennard-Jones potential. That's the classic theory to describe the chemical bonds, right? And then in 1965, a guy named Sladen, he made a modification on this Hertz model. Let's take a look at the Sladen model. That's Sladen's job. In the Hertz model, we are using two spheres to do the compression, but in more widely, we are using kind of probe, no matter in AFM or Rayleigh indenter. We're using this kind of cone-shaped probe to compress our samples. So this cone shape is different with the sphere. So for Sladen, he made some change. So he think about, that's my sample. And then I use a cone to penetrate my sample. So the contact area will be something like this. And his job is, I have the Hertz model S equals to 2AC times modulus. Stiffness is I can measure using force curve. Modulus is my holy grail, what I want. So his job is to get the AC out, the contact radius out. So for this one, he think, it's quite simple, right? So this is my cone. I know the half angle of my cone is alpha. And here is the deformation. So AC is deformation times tangent alpha. Right? Quite simple. Okay, so with this, he can write down his equation. So stiffness equals to 2 times deformation. The deformation, I would use delta to represent deformation. So it's delta times tangent alpha times modulus. And the S equals to the force divided by delta. So he put this delta on right side is the force equals to 2 E times tangent alpha times delta square. So he gets something like this. And the coefficients is due to the geometry we jumped at, but the point is the force is proportional to the delta square. That's the Sladen. That's the Sladen model. That's the typical Sladen model. Okay. That's his job. Okay. Then from that, people finally establish this kind of solution. So they think about this way. At Hertz model, my indenter or my stylus or my stylus is a sphere. And if I'm using a sphere to indent a sample, to indent my sample, and my sample, I think it's also sphere, but the radius is infinite, okay? So I use a sphere probe to indent my sample. I get the deformation at delta. And so his idea is to calculate the AC, the radius, the contact radius AC For this one, the AC, we know the radius of our probe. We know the radius of our probe. So the AC just equals to R delta root square. It's just the geometry. You can just do some calculations after the class. So we have the AC like this. And then I took it back in the Hertz model. So F over delta equals to the stiffness. And this one is 2 R delta times E. And so finally he get F equals to 2 root square of radius of the tip and times modulus and then times delta 1.5. For slider model, we are using a cone to penetrate my sample. And the contact radius is the deformation times tangent alpha. The alpha is the half angle. And finally, the F equals to tangent alpha times E times delta. Is square. And we finally, we have another common shape. It's column. So we are using some column to compress my sample. This shape probe is widely used in travel indenter. In the large indenter, you can make a pillow by yourself. For example, you can stick, you can glue a stainless steel column or stick onto the probe and to use that to compress my sample. This kind of is widely used in the large indenter. And then for this kind of probe, the contact radius is a constant. It just equals to the radius of your column probe. So the Hertz model will be quite simple. The force equals to the 2 column radius times modulus times delta 1. So after that, people made a summary. He found for a based on Hertz model, I can make a summary like this. So the force is proportional to my deformation. But the order on this deformation is based on the shape of my indenter. If I am using a column, the order is 1. If I am using a cone, next Snyder model, this order will be 2. If I am using a sphere, the order is 1.5. And the coefficient here is a function of modulus. So our idea is to establish the relationship between force and the deformation. And after that, people does not use the classic Hertz model. So they don't need to really calculate the AC, what it looks like. They don't care about that. It's just a function of the deformation. So finally, they will do something like this. They capture a force against the deformation curve, And the curve is something like this. And from this curve, they will use this model to fit this curve. And from this curve, from the fatalist function, he can define the order and the coefficient. And then from this, he can finally define what the probes looks like. And the coefficient is a function of modulus. So from that, he can get the modulus out. That's the key idea. And this one is used on nulling indentar. Because the probe, the stylus on nulling indentar is a certain diamond, right? The diamond is it's a crystal. It's hard to cut it into sphere or a cone or a column. No, it's the diamond is defined by the crystal structure of itself, right? Which corner you are using on the diamond. So for that kind of probe, it's hard to get the contact radius out directly. So it's hard to use some the mathematical game to deduct it out. So usually we will do this curve. We will do this curve, and from this curve we do the fatalist. We get the order, we get the coefficient, and then from the coefficient we can get the modulus out. That's we use on the tribal on the nulling indentar. That's the classic way. That's a classic way. Okay, but for AFM probes, the AFM probes is a kind of consumables. It does not require us to do such a good calibration as we done on the nulling indentar. So on AFM, usually we just do it kind of roughly on this step. Okay, so on the AFM, if we are using one of these specific shapes, we can directly use the theory. We can directly use the theory for this. Okay, so for example, if you are compress your cell or gel, your probe is always a sphere. I can directly use the Hertz model. If I am compress my sample using a cone, the AFM probe looks like a cone. I can directly use this model. Okay, so finally, we can make our summary. So our idea is out. We have the stiffness. We just need the AC. We just need the, sorry. We have our series. Stiffness is 2AC times E. We just need the AC and we can get the modulus out. So our idea is how to get the AC. So we have some options. So first options, if you are using a sphere, if you are using a spheric probes, some situations, for example, you are using a colloidal probe. You stick one sphere onto the probe using the sphere to compress your sample. Or you can use money to buy this kind of probe. The end side of your probe is already a sphere. On these two situations, the radius of your probe is defined. The radius of your probe is defined. That's just the radius of your sphere. And then the AC is root square of the radius times the delta. And then you can use the Hertz model directly. You can use the Hertz model directly. Okay? So the force is proportional to the delta 1.5. Right? The force is your measured. The delta is your measured. So you can get the modulus directly from the coefficient. Second, if you are using a cone shape probe, that's the AFM probe we are using. And then on this probe, it's just use the slider model. So the AC is the delta times tangent alpha. And then our curve will be the force proportional to the delta 2. The order is 2. It's proportional, right? That's another situation. So this situation is using a sphere. This situation is using a cone. And usually our AFM probe is not a circular cone, but a pyramidal. Our probe looks like this. And the broker offer a way to calculate this, to calculate how the half angle of our probes. And usually this half angle results is 19. Usually brokers is 19. Is around 19, right? And for other manufacturers, they do the similar jobs. So it's about 90. Okay, the third one is similar. If you are using your homemade probes, if it is a column, that's the simplest one. The force is proportional to the delta first order. That's the simplest one. But of course, it's not widely used in AFM. People usually do not use this kind of probe. Okay, so besides these three situations, we will face the same work on the Lalo indenter, an unknown shape. The unknown shape. So usually the unknown shape means something like this. So our probe is kind of pyramid. And we use the probe to compress my sample. So of course it is not a sphere. So I cannot use the Hertz model to do it. But the indentation or the deformation is so small, it does not penetrate my sample significantly. So I cannot use the Slider model directly. The Slider model usually, from his description, they should penetrate the sample. So it means the deformation, it should be very large. So usually for this Slider model, they require delta to be large. Usually in the reference, when it's over 30 nanometer or 50 nanometer, they think it's large enough. But if your deformation is so small, you cannot think this is a penetration. So you cannot use that model directly. So for this one, we need to do some calibration. That's the so-called relative method. That's the so-called relative method. Actually, the relative method is the way we use for Lalo indenter. Usually, we need to take a sample with known modulus. And then we do a force curve on this modulus. Since we know the force is proportional to a coefficient, and this coefficient is a function of modulus and times the delta n. So if we do a force curve on this on these non-modulus samples, we can get the coefficient out. And then with the coefficient, we can do a force curve on my own sample, and then I can get the modulus. This non-modulus sample on that null indenter is unique. It's just quarters. It's quarters. The quarters is a crystallized silicon dioxide. So its modulus is 69 gigapascals. So it's a known one. So usually when we do the null indenter, we need to do the calibration on quarters. But on AFM, the story is different because we are facing various samples. So the non-modulus samples on the AFM, we have other reference samples that the facility provide different kind of samples. Oh, sorry. Column. Force data. Okay. So the non-modulus samples provided by our facility, we have this kind. First, we have some PDMS. The modulus of the PDMS has been measured using the macro scales instruments. It's about 3 megapascals or 2 megapascals. And the next step is we have some polystyrene. The polystyrene, the modulus of the polystyrene is usually around 9.7 gigapascals. And then the next order, we have the graphene. The graphene we are using is the highly oriented. It's about 18 gigapascal. And of course, the next step is we have quarters. The quarters is 69 gigapascal. So we provided this 4 material. We provided this 4 samples as a reference. So before you measure your own sample, you can do a force curve on one of them. And from one of them, you can define your coefficient. And then after that, you can do a force curve on your own sample. You get the modulus out. That's the idea of this relative method. Of course, it requires us to define the order. And usually in the null indenter, this order should also be defined by the curve. But for AFM, we make it simpler. We just use 1.5. So we just use the original Hertz model. We think the probe is a sphere. And then we use that to define the coefficient. That's the AFM's relative method. Of course, it's not that accurate compared with the null indenter, but it's okay to use it. Okay, so that's this idea. Okay, so Brooke provide another way. You maybe heard it from some of our engineers said, we have a so-called absolute way to do it, but it is not that accurate. They just use a sample to get the geometry, of our probe, and from that geometry, they simulate the tip radius out from this shape, and that's the so-called the absolute method. But to me, it's not that accurate. We prefer the relative method. Okay, we prefer the relative method. So I think that's all about the contact mechanics. So basically, we're starting from the Hertz. We're starting from the Hertz model. We establish a relationship between stiffness and the modulus. The whole idea is we need to figure out the contact radius. So for the contact radius, we can use the geometry of our probe to figure out the contact radius. We have sphere, we have cone, we have column. If our probe is not a specific shape, we need a relative method to get it out. Okay, so that's the whole idea of the contact mechanics. So after that, you get the stiffness out, you get your shape, you have the modulus. That's our final. That's the holy grail we are seeking for. Okay, so that's about the basic concept of the AFM nanomechanics. And I think in the afternoon we will do some hands-on sessions. We will show you the calibration stuff. We will show you the capture of force curve and transfer the force curve into our stiffness. And once that in the software, you can choose your contact model, and then the software will give out the modulus. That's about the whole idea. Okay, so that's the about the force curve part. So we will have some hands-on session for you to do the practice. And if you have your own sample, maybe we can do a simple demonstration. Okay, so we have about half an hour, so we will jump into a Brooker's technique, so-called PeakForce QNM. And the PeakForce QNM is just use this theory to make to capture a distribution of modulus and use a quicker way. Okay, so the next part of my slides is just about the softwares. Is we will demonstrate on the hands-on session. Okay, PeakForce QNM compared with this kind of force curve, I think it's less scientific. It's more about introduce the technology about this one. So I would say it's more like to introduce a technique, and you understand the principle of this technique, and to say if it can provide the results you need. So we leave our roadmap here. So again, we always capture vertical against the Z. That's the force curve. We need to define. We need to calibrate the differential sensitivity. We need to calibrate the spring constant, and then we combined with the shape with the Hertz model. We can get the modulus out. That's our roadmap. Okay, of course, AFM cannot measure Poisson ratio. We need to provide Poisson ratio. Yeah, that's AFM cannot do it. We require people to provide the Poisson ratio. Okay, so the next step is about the PeakForce QNM is to find a way to get the modulus mapping. So our idea is also starting from the force curve on each we do a force curve on a certain point, then we can get the modulus on this specific point. But I have my sample. Usually my sample is made up with several components. And for example, we have the, let me think about, uh, yeah, for example, we have a alloy sample. Yeah, we have some irons, we have some tin. Okay, then my idea is to find out the distribution of the tin and iron on my sample. So my idea is I can do force curve mapping on my sample and to find out which part is hard, which part is soft, and then I can get it out. So my total idea is if I can do force curve on each point of my sample, and then on each point I can get a modulus out, and then I can get a modulus mapping. On this mapping, it's not morphology anymore, but instead it shows the value of the modulus. So this part is high modulus. This part is no modulus. I'm sorry, this part is no modulus. And then I know my sample. This no modulus should be T. This high modulus should be iron. And then from this modulus mapping, I get the component mapping. That's the idea of the modulus mappings, the purpose of the modulus mapping. Of course, if you just need to get the components mapping, you don't need to know the accurate modulus value of tin or iron. You don't need to make this step accuracy, right? People know the modulus of iron. People know the modulus of stiffness. They don't need you to tell them. So in such case, you don't need the accurate calibration. You can just type in certain value provided by the manufacturer or the software. You can just directly type in a value, and for the shape, nobody cares. Just type in any value, and then you can get a inaccurate modulus mapping, but does not matter. It still gives you which part is hard, which part is soft. That serves your purpose. Okay, but if you, as I said yesterday, if you invent a new 2D materials and you need to know the accurate modulus of these materials, and you need the accuracy. So this calibration is required to be done carefully, and then you can get the modulus mapping. And of course, this modulus is accurate. So if the calibration is required to be done carefully, it serves your own purpose. Okay, so before we do that, we need to think about it carefully. Yeah, we need to think about it carefully. If you really don't need the accuracy, please do not waste your time on the calibration. Calibration, as we will demo this afternoon. If you want to do it carefully, yes, it requires some time, and it requires you to prepare your samples very carefully. But if not, no, jump it. Just type in any value. Okay, so the idea of the PeakForce QNM is just help you to do the force curve on each point quite quickly, and then we can get the modulus mapping. So let's take a look at the first curve, at the force curve. So the force curve, it consists of approach and retract. And if we draw and this y-axis, I just write down force. And the x-axis is z. Okay. Oh, I'm sorry, vertical. Okay. But if we take a look at this z against the time carefully, we can tell if our z against the time, our curve should be something like this. I'm traveling down, I'm traveling up. Okay, that's my curve. So usually the speed, usually the time on the force curve, if you may have done this experience many times, usually this time is about 1 second. Yeah, this is about 1 second. And in the parameter we said, this is about 1 hertz, means 1 curve per second. So the time is about 1 second. So if it is 1 second, let's think about an image. A typical AFM image, the resolution is about 256 times 256. So if we capture a force curve, each force curve, it requires 1 second. So the total time is about 60,000 seconds, right? 60,000 seconds is all over 1,000 minutes. The 1,000 minutes is over maybe over 200 hours, something like that. So this is just one image. For one image, it requires you over 2,000 hours. That's not acceptable. So we cannot accept that. We need this force curve to be fast. So this force curve to be fast, and when we take a close look on this force curve, we found some problem. Is here. In high school, we know the Newton's law, the first Newton's law. The first Newton's law told you are facing an inertia, right? So the probe is moving down. And then you ask the probe is moving up. So the Newton's law told you cannot change the direction, or you cannot change the velocity that easily, right? You need to add some force. That's the Newton's law. So when you do this force curve quite fast, you may face, let me think about, let me find out no way. Oh, I'm sorry. I don't have that. I don't have that slide, but it's okay. I can draw it. So when you do it in a quite fast way, you may face the Newton's law. So you want this probe to turn around at this point, but it cannot always follow your order. It will go down. And then it may go up. That's the real force curve when you do it fast. So this difference in the AFM community, they call it overshoot. Of course, this overshoot is due to the Newton's law. Okay, so as your speed increase, the overshoot will increase, and the overshoot will cause what? So that's the z movement, and then when you change it into the vertical over z. Our idea is we want our probe to turn around at this point, but as we said, it will have the overshoot, so probe will keep going. after a while, it can go back. So usually when we do it in a quite fast force curve, we will capture a force curve, some force curve like this. This is the maximum force we set, but the actual maximum force will be larger than the force you set. If you're, I'm sorry, do I have some certain thing? Uh, mm, I have a paper or something. Mm. Okay. If the consumer will have one. Okay. So, so if we have, for example, if we have a cell, if we have a cell, we want to measure the modulus of your cell. And for example, your experience told you the cell can only hold 10 nanonewton, can only hold 10 nanonewton. After 10 nanonewton, your probe will penetrate your cell and kill it. Okay, so you set your force to be at 9 nanonewton, and you think it's safe. But if you do it faster, the real force will exceed your your setup, and once it over 10 nanonewton, it will damage your sample. Okay, that's the key point here. So of course, if you said my sample is not that fragile, I'm just do the modulus on quite hard materials like 2D materials, I don't worry about that. But again, we need to think about the probe itself. Our probe is made up with silicon or silicon nitride. It's also kind of fragile. If you compress it hardly, it can damage your probe also. So the overshoot, it still will harm your probe or harm your sample. So our key idea is how we can reduce the overshoot, in the force curve. Okay, so since the overshoot is took place when we do it quite fast, so ideally when you do force curve, you want to do it slow. But if you do it slow, you cannot do mapping. So that's the idea here. So when we go back to this one, to the force curve, we realize the problem, the problem came out here. We have a velocity up, down, we have a velocity up, and then we have a large acceleration at this point. So that's the problem here. So if our velocity can be reduced to 0, then we conquer the Newton's law. We can just get rid of the overshoot. So the point, so the solution out here is how we can reduce the velocity to 0 at this point. So we think about it. So if our velocity is a constant, of course we cannot do it. So we will do some movement with acceleration and the deceleration. So the final solution out is we're using the sinusoidal movement. So with the sinusoidal movement, we write it down like this. This is the Z, this is time. So we make up a new movement. The Z, we define it as amplitude times, let me think about, cosine omega t. Let me think about. No. I should be sine omega t. Okay, the Z is a sine omega t. Once, then I can write it down. Okay, let me think about the T. The T equals to 0. The T equals to 0. No, I'm sorry. Should be cosine omega t. Yeah, should be something like that. I make up my movement and something like this. My z against the time is a times cosine omega t. I make it a solenoid movement. And with such function, we can take a look at the velocity here. So the velocity at each time at the at this lowest point, the lowest point is my probe touch my surface. So the velocity here is the z is the first derivative of my z, which will be a omega sine omega t. So at this, at this point, it will reach 0. That's the whole idea of my setup. Instead of the constant velocity, we change it into this solenoid movement. And as such, when the probe reach the surface, touch the surface, its velocity dropped to 0. As the velocity dropped to 0, it will not be such, there will not be such overshoot on the sample. So I can control my force quite accurately. So that's this idea. So no matter how I change this velocity, how I change the frequency, it does not change the velocity on this point. It's always 0. So we can increase the omega. And once you increase the omega, you reduce the total time, and then you can do it quite fast. And usually in the common setup, the omega is around 2 kilohertz. So the 2 kilohertz means you can do a force curve 2,000 times. You can do force curve 2,000 times per second. And then to capture 256 times 256 is around 4 minutes. That's acceptable. And that's the normal speed you used in the normal AFM setup. Okay, that's the total idea we have for this tip motion. We are using a solenoid moment. Okay. Now with this setup, we may continue to how to use this setup to help us to do the imaging. Okay, so let's think about we have a sample. We are doing a step sample. The step height, the step height, we set it to be 100 nanometers. And then we try to capture an image of this sample. So we do the setup something like this. So our probe, the initial point is our probe is somewhere here. And the distance between the, I'm sorry, not this way. Let me, okay. We can see it, right? The step height is 100 nanometers. The probe is somewhere here. I assume the distance between the tip and the sample is 150 nanometers. 150 nanometers. Now my idea is how can I capture the morphology of my sample using force curve? So my setup is like this. Once the probe touch the surface, I would compress my surface. I would compress my surface, and my force will increase. So my setup is like this. I assume my sample, the modulus of my sample is infinite. So it means it cannot compress my sample. So I would assume once my force reach 1 nanonewton, that's my maximum force. So I would assume on each point, I would do a force curve, some force curve like this, and the maximum force is 1 nanonewton. Okay, and the distance my probe will travel is 150 nanometers. Is 150 nanometers. That's right. That means once my probe reach the maximum force, it will retract 150 nanometers. That's my setup. Okay, then I use this to try to capture the morphology of my samples. So my probe is somewhere here. It will move down. Since my sample is infinite stiff, once the probe touches the surface, it reach 1 nanonewton, it will move back. Okay, so I set up my move back is also 150 nanometers. So once it moves back, it's also here. And then I make my probe to jump on this side for a step. And then my probe is going down and going up again to this step. And then it jump down, up. Okay, continuously. Once I reach this point, so my probe will going down, but my step is, will going down and reach the step. It reached the second step, so the probe is, so the blue curve, the distance of the blue curve is only 150 minus 100. It's only 50 nanometers. And it reaches 1 nanonewton, and then the probe will go up. It will go up as my setup. It will travel 150 nanometers. So the probe will go here. And the distance over here is 150. So my probe is here. Now it will jump. It again goes up 150, goes up 150, and then keep going up, keep going up, keep going up. And finally, I did many force curves on these steps. And then I get my idea is next. I take a look on this point at maximum force. It looks like the probe just touched the surface at the force, as I said, 1 nanonewton. And then my idea is to capture all this 1 nanonewton point. I connected them one by one. This will be the morphology of the sample. Right? That's my idea. That's my idea. I use the 1 nN force. I use the 100 nanometer setup. I do the force curve on each point. Once I finish one point, I jump a distance and do another one. I jump a distance, do another one. If you want this morphology to be quite sensitive or high resolution, you can reduce this jump distance to as small as you can. If you jump it, if you jump just say 0.1 nanometer, the resolution will be quite high. Right? That's the whole idea, is using the force curve to do this, to do the morphology of our sample. Okay, so the morphology we get is the when we reach the force at 1 nN. That's our idea. That's the force curve. Okay, so our idea now is we need to do it fast. So the speed here is we spend time on this down, up, down, up. We want to increase the speed at this step. So we change it into the spheroid movement. We change it to the spheroid movement. Okay, once we change to the spheroid movement, we found a little bit problem here. That's the A. Our A, we have to make it a constant. That's a spheroid movement. If you want to make a sine wave, the amplitude, you have to make it a constant value. But when we take a look at the force curve, the only one we want to take out is this one. We compare this force curve, this one and this one. Let me draw it carefully. That's my step. That's 100 nanometer. At this point, the force curve should be the blue curve travels 150, and the red curves travels back 150. Okay, but when I reach this point, the first point on my step, the blue curve can only travel down 50 nanometers. It will reach the step because the step is 100 nanometer taller. So when I draw force curve on this point, it will look like this. It moves down 50 nanometers. It will reach the step. It will reach the 1 nanometer. And then the red curve needs to travel another 150 to here. So in this setup, the blue curve and the red curve, the traveling distance is not the same. It will depend on the topography of the sample. So that's why the blue curve after this first curve, it will be somewhere here. That's the total idea. I can drag the probe up. So as I said, as our setup, I only control the traveling distance of the retract part. I do not care about the extend part. The length of the extend part can change. Only the retract distance is fixed. That's the idea of the force curve. But this idea cannot be used for my spheroid movement because the amplitude of the sine wave is fixed. So our idea is how we can apply this idea for this step. Okay, so this afternoon we will explain this part, and after that, you can know how the PeakForce QNM or the PeakForce tapping is moving, and then we can better to use it for our modulus mapping. Okay, so we stop now, and we will go back at 2 or 1:30. 2. Okay, so we will go back on 2, and we finish the PeakForce tapping movement. Then we can jump to the hands-on session. Okay, hands-on session is on second floor. Yes. Okay. Okay. Thank you for your time in the morning. It's just uh, it's a little bit long story about the mechanics, and the afternoon we will be more focused on the people's typing movement. Okay. Thank you so much. Thank you. Okay, let's continue with the imaging part. So our key idea is we apply the force curves and use the force curves to do AFM images. So basically, we just want to scan an area, and on each point of this defined area, we want to do a force curve. And then from the force curve, we do the analysis to capture them to get the modulus out from the force curve, and then we can get a modulus mapping. That's our total idea. And so we can use the force curves ideas and to do this mapping. So idea is we define a maximum force and we define a retract distance. And then use this idea, we can do a force curve mapping. And this force curve mapping is, and we show this kind of example. And since the force curve only defined the retract distance, we do not define the extend distance. As such, we can capture this kind of the images using the force curve. But the problem is the force curve, we cannot do it quite fast due to Newton's law. We have to reduce our the speed of the force curves. As such, we cannot increase the speed, and it took a long time to capture an image. So we think about another idea. We use sinusoidal movement. We use sine wave. As such, at the point the probe touch the surface, the speed will reduce to 0, and then we don't worry about the inertia. So that's our idea to do the so-called peak force. Okay, so under this kind of movement, since it's a sine wave, we need to define frequency, we need to define amplitude. This should be defined, and as such, we can have this kind of movement. So with defined amplitude and frequency, when we take a look at this kind of image, and we may see some difference. So okay. So okay. So again, we have this kind of sample. The distance, we have a step sample. The height of the step is still 100 nanometers. For this one, we still use the force, maximum force. We set it to be 1 nanonewton. And the sample, we set the modulus to be infinity. And then for this one, we mimic our example in the morning. So we assume the amplitude is 75 nanometers. So amplitude is 75 nanometers. So from the top to bottom, the distance is 150 nanometers. Is the same as this example. Okay, so we assume our starting point is somewhere here, and this distance is 150. So we can start the force curve. So it's going down 150. we reached the bottom, and our force dropped to 0. It's good. And then we retract 150, and we go back to this point. And the same principle as we did here, we have a jump. Okay, and then down, up. It's as simple as the example we have in the morning. So finally, we reach this point. Now, our blue curve is the approach. It goes down 50 nanometers, and then it reached 1 nanonewton force. And then what's going on? Should it going down or should it retract? According to our principle here, we wanted to retract, but this is a fixed sinusoidal movement. We already set the amplitude to be 75, so it cannot go back. It has to finish the 150 movement. So our probe should continue going down until it reaches here. And then we take a look at the force curve here. So at this point, the force curve is quite simple. It's 150, and it reaches 150. And the force, it can reach 1 nanonewton. No problem. And on this one, as we said, once I move 15 nanometers, I already reached the surface. So I already reached 1 nanonewton. But the amplitude is fixed. I have to go in down. So the force will continuously increase to a certain value is not controlled. And then it goes back. And then it goes back. And since once it goes back, it still comes back to this point. Now the difference came out. In this one, it will retract once it reaches 1 nanonewton. But for this kind of peak force tapping, but for this kind of peak force movement, the sine wave movement, the amplitude is fixed. I have to finish this amplitude. So we sacrifice the force. So my force is already larger than the 1 nanonewton, my setup. So we will use another logic to do this kind of this kind of imaging. So if we do not move, if we still make our probe here, once it jumps, it will keep doing this. Then my force setup is sacrificed. Actually, the force is significantly larger than 1 nanonewton. So we change this to a feedback. So I will erase this part. Let's keep this one. So my feedback idea is we used in the imaging. For example, for your AC, for your air conditioner, it's just using a feedback concept. You set, for example, you set this room temperature. You give a set point of the temperature. For example, you want the 20 degrees C. You want your 20 degrees C, and then we have a sensor. This sensor can read the temperature of the room, and then we get a difference between the sensor out and the 20 degrees C. So it can give TS minus 20 degrees C. And then we use this to control the power of my air conditioner. Then I will use the difference to control the power. If it is larger than 0, it means I need to give out larger power to reduce the temperature of my room. So I need this to control the power of my chiller. And then the chiller moves, the chiller is working, it can reduce the temperature at this room. That's how the air conditioner is working. So until the temperature sensor read the temperature reaches 20 degrees C, it means it reached your set point, then the chiller will stop working. That's how we control the temperature in this room. So I want to use the same concept to do this. So my whole idea now is I found I want my force to be set at 1 nonewton. But if my surface is the height of my surface increase, my point is if I still want the force to be 1 newton, I have to lift my probe. Right? I have to lift my probe. As such, once it travels this amplitude, once it travels down the 170, 150, I still touch the surface. I reach the 1 newton. So my setup is this. I still gave a setup, but this time I give the setup is peak force. The peak force means the maximum force on each force curve. The peak force I set, for example, I set it to be 1 newton. And to reach this peak force, I have to travel a fixed amplitude. For example, at this case, amplitude is 75. So it has goes down or goes up 150 for each circle. And then I will capture a real-time peak force. I again take the difference with them. From this distance, I will use it to define the position of my tip. If it is 0, if the error is 0, means my probe is in the right position. I travel down 150 nanometers, I can touch the surface. If it is larger than, if this difference is larger than 0, that means my probe is too close to the sample. I need to move it up until it reach 1 newton. Until it reach 1 newton. And as such, I can use this to control the real-time peak force. For example, in this example, at this point, once I going down 150 and going up 150, my peak force is significantly larger than 1 newton. So this mechanism will work, the tip will go up until the distance is 150 again. And then at the next step, it going down, going up, the force curve is like this one. So that's the mechanism, we call it feedback mechanisms. So if we compare this one and this one, we will say this one, we always make our force at maximum. We always make the maximum force at our setup. But for this kind of feedback, we may have several points. It missed the setup. But the good thing of this kind of mechanism is we can make it fast. But this one, no, it's kind of slow. It depends on the speed. But this one, yeah, we sacrifice several points force, but the good thing is we make it fast. So that's the feedback mechanisms of the PeakForce tapping. Okay, so we as such we can do the force curve at each point quite fast, and to get a nice images. And I know we have some users now here. They are using the JPK, and on that machine, you may not use this kind of PeakForce tapping very much. You may use the mechanism similar to this. You may similar to this, and in JPK it is called QI mode, and the QI mode, it's the mechanism is something like this. And in QI mode, what they are doing is they just take overshoot. So they just accept overshoot. I want to make it fast, and I will accept I have a large overshoot of force. I may sacrifice the sample or tip, but I want to make it faster. So that's the mechanism on the JPK. But for this dimension icon or dimension XR system, we will use the PeakForce tapping. And PeakForce tapping, we can do it faster. And the difference, we use the feedback mechanisms. Okay, so that's the two ways to do this kind of mapping on each point. Okay, so then the next, they are all some details, but the key point is we need to understand the feedback. Okay, so the peak force. Okay, so we write it down. Here is my Z over time. So the Z over time, the function is Z equals to A cosine omega t. Usually, omega is about 200 kilohertz. Okay, so let's think about the force. I'm sorry, vertical over time. So our probe is moving with our scanner. Now the scanner is moving such fast, moving up and down, up and down. And at the same time, the cantilever will move with the scanner up and down, up and down, up and down. So the probe has a, the cantilever, it has a speed. So under the speed, it will sense a hydrodynamic force. The hydrodynamic force is usually eta dz over dt, right? It's just a kind of friction. So when the speed is large, our hydrodynamic force will be large. So we are moving in this way. So the friction we sense, we may also change it according to this one. So it will be negative eta, and since this is cosine, so I have omega out, and it is a sine omega t, and there will be a negative out. So this one is positive. Okay, so that means the probe is moving down. The Z is moving down. The probe will face a force up. So according to this one, so when the probe is moving down, we will have an increased friction or increased hydrodynamic force. So it's like this. Once it reaches the bottom, once it reaches the lowest point, the friction will drop to 0. And then, I'm sorry, try to make the same period. Yeah, something like that. And then when the probe is moving up, it will sense hydrodynamic force is facing down, right? Something like that. So this is how the Z change. This will be the hydrodynamic caused vertical change. And we know we have a sample beneath our probe. So the probe will touch the surface. It will have a force curve, something like that. Right? It will have a force curve, something like that. That means there should be a sample around this area, around this region. So we combine this force, we combine these two forces together. We will get something like that's the force curve we would observe in principle. Okay, this is the hydrodynamic force plus atomic force. That's the original force curve we get, and that's this night showed. We may observe this kind of things, but our point is we only want to observe the atomic force. We don't want the hydrodynamic force to be the dominant one. So the idea is we want to get rid of the hydrodynamic force. So this one is the so-called the background subtraction. So how we do it? So Brooke, think about this idea. Think about a way to do it. So the idea now is I just want to get rid of the hydrodynamic force. If we can subtract hydrodynamic force from the force we captured, we want to get our ideal force curve, a completely plane background. Right? That's our ideal force curve we want to get. So how we do it? We need to subtract the real vertical value from the we need to subtract the background from our the background from our vertical value. So the Brooker think about a way called lift. For example, this is my sample, and I assume my probe is somewhere here. So it's moving down, moving up, and it can capture a force curve like this. And then he want to substrate the background. He need to get out the background first. So the idea is, if I lift the probe by a distance, and then when it moving down, moving up, they would not touch the surface. And then the vertical change against the time will be pure hydrodynamic force. And then our software will record this one. And then for the vertical value I captured each time, I subtract the background, and then we can give out the ideal force curve. That's how the software is working in the background, and this one is called the lift. And there is a parameter named lift height. It's used to define how tall you want to lift it up. Of course, this one should be as small as best, because if it's too large, the background may not be accurate. But this idea may not be always working well, because we know our surface can change variously. For example, if we have some samples like this, we have I draw it here. If we have some sample like this, there will be a quite deep there will be a quite deep valley on my sample, and then the background here. The background here and the background here, they may be different. Because, of course, the hydrodynamic force may be the main component, but the viscosity can be changed due to the sample environment. So the background, we cannot assume the background is always the same. So for this kind of thing, we set the lift height maybe here, we capture the background here, but the background cannot be applied correctly in the valley. So the lift height mechanisms imply we have a constant background. This may not be always true, especially for those kind of valley or peak samples. So Bruker provide another idea. Another idea it's not opened by default, but we can try in this afternoon. It is called dynamic background removal. And the dynamic background removal is pure science. It's pure mathematics. His idea is this. So if my theory is correct, the hydrodynamic force is just a pure solenoid wave. It should be something look like this. So I just need to get this curve out, and then I can substitute it. So his idea is using the algebra named actual potential. So he think about it in this way. So this part is the sine wave. This part is also the sine wave. Only the central part is mixed with the atomic force. So if from this real time, the vertical value, I cut the central part out, I gave a force curve, something like this. And then I use the algebra. I use the actual potential mechanisms. I can mimic this part. And this one should be a perfect background. And then I use this one minus my background. I should be able to get the background removal done. So this one is pure just use the mathematics to get the job done. And when you open the dynamic background removal, you just need to tell the software how many parts of the force curve you want to mask or get rid of them. And then the left part will be used to apply the actual potential mechanism. And we can show you this afternoon about about this mechanism. And I myself think this is a quite smart way, and it may work better than the lift mechanisms, especially for those peaky or valley samples. Okay, so this is about background removal. Okay. So after this, after background removal, we may have another thing needed to consider. It's the so-called ringing. Ringing is also easily to observe during the PeakForce tapping. And this ringing, let's go back to our to the morning session about when a probe exists in the in a viscous environment, or we need to consider the hydrodynamic force. The force will be the Hooke's law and the hydrodynamic force. And finally, we will get a damped oscillation, right? We will get a damped oscillation, deflection against time. We will get a damped oscillation. Do we have a ruler or something? Do we have a ruler or something? 尺子. We may be able to show you with a ruler or something. Yeah, this one is also okay. Yeah, this one is also okay. So if we think this is a cantilever, and once you bend it significantly, you release, you can say it's vibrating, right? It's vibrating. And this vibration will be follow this kind of equation, right? You give a force, it has a stiffness, it will have a spring constant, so it will stand a Hooke's law, but it is vibrate inside the L, it will give a hydrodynamic force. So its vibration will be damping, right? So it will be follow this kind of damped oscillation, something like this. So when we do a force curve, and we reach this bottom. This is the adhesion force. And then after the adhesion force, our probe is trying to moving up. And then it will get rid of the adhesion force. It will be similar like I bend the probe to the bottom and then I release it. It will start to do this kind of damped oscillation. So we may observe something like that. And this one will be easily observed in the PeakForce tapping because we do this force curve in a very in a very fast way. So just like if you bend it slow, it will stop. The oscillation will stop quite fast. But if you do it this fast way, you can see this damping. So that's the origin of this ringing. That's the origin of this ringing. So from this curve, if we remember the morning's function, the deflection equals to a certain amplitude times E. This one will be omega 0 divided by 2qt. And then the another part is EI root square omega 0 square minus omega 0 divided by 2qt. Yeah, that's our results. So if the Q is quite large, then this one will be quite, it will decay quite slow. Then our curve will be something like this. It decayed or it damped quite slow. So if we are using a high Q probe, which will be mainly your tapping probe, such as the TESPA 150 or another famous, or if some researchers, they will do some electric stuff, for example, the SMPIT. For this kind of high Q probe, the oscillation will never stop. You may observe force curves like this. You may say this kind of damped oscillation, it's always there, something like this one. Okay, this is caused by we call this phenomenon raining, and it is caused by the damped oscillation. Okay, so usually we are using some soft probe, for example, the scan assist L. Scan assist L, the Q is quite small. When the Q is small, it will damp quite fast, and then you may say the raining just do 1 or 2 periods, then it's done. But if your Q is large, you may observe this kind of thing. Okay. So when we have raining, when we have this kind of raining, we may face a problem. So the peak force, let's assume we already removed the background due to the hydrodynamic force, and then we only need to face the raining. Okay, the next thing we need to think about our feedback. Our feedback is we capture this peak force. We compared with our set point. And then we use this to drive our probe moving up and down to finish the feedback mechanisms. Okay, so the point here is we need to capture the vertical value or the force value at this point. Then the question is how? If we just use some certain mechanism or certain algebra, we just took the maximum force in one pyramid, we may face a problem at this raining situation. Because raining is so strong, it would exceed the atomic force. So, for example, in this example, the maximum raining force is really large, but the atomic force should be somewhere here. So it means we should not use the maximum inside one pyramid, inside a period. That's our the problem here. So the broker they choose a smart way, or they choose you can say it choose a lazy way. Just inside one period, in period, the z equals to a cosine omega t. For defined sine wave, the lowest point should be reached at a defined time point. For example, if my omega is 2 kilohertz, I should be able to reach the lowest point at 250 microseconds. Right? The 2 kilohertz means it's pure in its period, it's 500 microseconds. So at 250 microseconds, I should be able to reach the lowest point. Then I don't need to worry about to use some certain mechanism to find the maximum force. No, I won't do that. I just to rate the force at a fixed time. So that's the idea used by Brooker. And this idea, they call it synchronous. They call it synchronous. And this time point, Brooker gave a stupid name called sync distance. It is the time, but Brooker called it distance. It's just maybe for them it's a smart way to let nobody knows what they're going on. So this sync distance is actually a time, and it defines at which time point I reach the lowest point. I reach my peak force, and then I rate the vertical value at my defined sync distance. Then I don't need to use any mechanism, any algebra to calculate the maximum force. No, I don't do it. I just take a value at a certain time point. And that's the sync distance. And with that, we can easily to do the feedback thing. Okay, so that's the whole idea of the PeakForce tapping. So we use the feedback mechanisms, and we use a background removal technique, either lift or dynamic, and then we define a sync distance. We took the vertical value at the defined sync distance. I gave it back into the feedback mechanisms. It can give me the probe distance. I'm sorry, it can give the probe position. And from the probe position, I can do the game to get the morphology. And since it's sine wave, the speed will be 0 when I reach the lowest point. Then it's good to go. Then the game is done. So that's the Brooker's PeakForce tapping. Okay, so once we get this done, we combine the force curve stuff. We calibrate spring constant. We calibrate this deflection sensitivity, and we defined our contact model to define the contact area. Contact radius, and then we can get the modulus at each data point. And of course, if you want, it can give you the adhesion force. And with that, it can give the mechanical property mapping. And in the Brooker software, it can give you many different property mapping. For example, they can give you the deformation mapping. But the deformation is not meaningful to us because we have modulus. That's it. We don't need the other stuff. And they have the so-called dissipation. The dissipation is similar to the adhesion force. That's the blue curve. That's the red curve. And it will be some loop. It will be some loop between red and blue. And we think this one means the so-called adhesive work. And Brooker gave it another name called dissipation. Just the looped area. Yeah, but besides that, but usually researchers just take modulus and adhesion force. They don't worry about it. Brooker's other stuff. Okay, that's our PeakForce typing. So the let me say. Yeah, that's the PeakForce typing, and from the PeakForce typing we have the so-called PeakForce QNM. The QNM means quantitative nanomechanical mapping, and it gives the different things. For example, it gives the adhesion force mapping. It gives the modulus mapping. It gives the deformation mapping. It gives the dissipation mapping. But the useful thing is modulus and the adhesion, right? So that's the main part of the PeakForce QNM. And for the when we really use it, we can explain more during our hands-on session. But we need to explain some more calibration we need to use here. Let me figure out the part. Sorry. The switch slides. Okay. So for this slide, we want to introduce more about the synchronize or sync distance. Brooke invented this technique in 2009, I think, 2009. And then it released this this technique. Then, and I think after 3 or 4 years, and our users gave us some class and told Brooke, you guys did some stupid thing. So on our next lectures, we would start to talk something about the viscoelasticity. The viscoelasticity is a quite wide the property, especially for those polymer materials. For elasticity, the idea of the elasticity is to figure out the modulus. And in elasticity, we would imply the modulus is not a function of time. Means our modulus should be some constant. Once your material is fixed, the modulus should be a fixed value. It will not change against time. You measure for example, you measure the silicon, the modulus of silicon. Today you capture the 165. Tomorrow you should also get 165. After 1,000 years, you should be always 1,000 165. That's the elasticity means. It has nothing to do with time. But that's not always true for those kind of soft materials. For example, for polymers, we know the polymers inside the polymers is just a lot of the molecular chains. And it's inside the interaction of this chains, it will change against the time. So the viscoelasticity means your material, it looks like, or it has the property of fluid. The fluid has the viscosity, and or in other words, your modulus or stiffness is a function of time. It can change against time. So for example, you may also know something like water. And nowadays, we can use quite fast speed cameras to capture the water. Once you may also see that kind of video on YouTube. You see a water drop when it drop down and to reach the surface of the, say, a water or sea. First, the water droplet drop on, this is water. This is also water droplet. When it reaches the bottom, those kind of high-speed camera can say, it first, it looks like a solid. It will bounce back, right? And then it will reduce its speed and finally it immersed into the water. And I think I can find the video and show to you later. So that means everything it can express both viscosity and the elasticity is we need to consider the time as a function. So the modulus or the stiffness is a function of time. And so for this kind of materials, we need to think about its force curve. So for example, we assume we have some material like cell. Once you compress your cell, you can sense your cell is getting softer and softer and softer. So we assume it's the modulus or stiffness, it will change against time. It will be softer and softer and softer. So now we are doing force curve. We are doing force curve. I compress on my cell. I reach my maximum force. And then I assume I do my force quite fast. And then the cell, I did not sense my cell is getting softer. I already retrace back. Then it's quite easy. But if I do my force curve, quite slow, when I compress my cells, I compress the cell, the deformation will increase. So I would sense my force equals to the stiffness times the deformation. The deformation will increase with my probe, with the J increase. But at the same time, the stiffness is reducing against the time. If I do it slowly, then we would say our force curve is something like this, right? It will increase quite slow. It will increase quite slow. Right, that's the force curve we expect to get for those kind of cells. And I think some researchers may say this kind of force curves many times when you're doing the cell or gel samples. And then it will retract. Something like that. Okay? Then for the let me think about. Okay, so if let me think. Okay, so for the fourth curve, the logic is quite simple. We only need to reach a maximum force, and then we can get back. That's the fourth curve logic. In PeakForce typing, logic, this is also force, this is the Z, then the logic may not be the same as this one because the distance we travel, is a fixed value, right? The Z equals to A cosine omega t. The distance we travel is a fixed value. So the probe will go compress the sample. And let's consider a situation. If the stiffness is dropped to if the stiffness is dropping quite fast, if the stiffness is dropping quite fast, and once we reach the distance, once we reach this 2A, once we reach our set distance, the sample is already getting quite soft. So we may have a force drop. Force drop. That's for some quite visco. For some samples has very high viscoelasticity. It means its stiffness dropped too fast. And once we finish this 2A distance, the sample is already be so soft, and the force may drop. And then once it reaches this 2A distance, my probe is retracted back. The fourth curve I get is something like this. So that's maybe the real force curve I captured for some viscoelasticity samples. And then for this kind of force curve, I need to think about the so-called sink distance. I need to think about the sink distance. So ideally, my sink distance from my definition, the Z against the time, the Z against time is something like this one. It's something like this one. So the sink distance by definition is the time point. It's the time point I reach the lowest point, and then I change the direction of the Z movement from approach to extent. That means this point. That's my sink distance, the purpose meaning of my sink distance. And we assume our sample is elasticity. If the sample is elastic, When I reach the lowest point at the Z, I should reach the maximum force at force curve. So in 2009, when Brooker invented this technique, they assume these two times is the same. But for the viscoelastic samples, if your stiffness is dropped quite fast, we would get some force curve like this. When I reach the lowest point, the sample is already get soft. The force dropped. And so this should be in our definition. This one should be the sink distance. This one should be the, by definition, this one should be the sink distance. But in PeakForce technique, in old technique of the Brooker, they assume these two lowest point in Z and the maximum force the maximum point in force, they are the same. So the old Brooker technique will make this one as the sink distance. That's something wrong for the viscosity samples. So nowadays it changed it changed the techniques, but it confused our users. In the nowadays techniques, we have a so-called sink distance nu. The sink distance nu is for the maximum force point. And the original sink distance, the Brooker gave it a name, sink distance QNM. It is used to define the lowest point of the Z. So if we need to do the peak force, we need to figure out this sink distance. That's why we do some calibration in our setup. So that's the two sink distance you may see during the hands-on sessions. Okay, so that's the thing we are facing. Oh, let me check my slides. Okay, so the same as the force curve, we need to calibrate deflection sensitivity. We need to calibrate the spring constant, and besides that, for the peak force tapping, for the peak QNM, we need to figure out this sink distance QNM, so-called sink distance QNM. And besides that, we have another thing need to calibrate is this Z. And for Z, for peak force tapping, we defined Z equals to A times cosine omega t. And this the amplitude value defines the distance we are traveled. And for the peak force tapping, we need to calibrate this value. That's the so-called the drive sway sensitivity. But it's done on the softwares automatically. So basically, we can in the software sessions. Why it's so? Yeah, we can have this kind of calibration windows. In the calibration windows, we will do the similar things. In the morning, we do the thermaloids to calibrate the spring constant, and we do force curve on sci-fi to calibrate the deflection sensitivities. And the last step we need to do is to capture the sink distance. So that's the calibration window in the softwares, and we can see it. And in the afternoon, in the hands-on session, we can see those kind of things. We have a QR code to scan the probes. The probe is already calibrated. The K is already calibrated. We can to scan it and capture the K. And the end of the tip is a sphere. So the radius is also calibrated. It makes the calibration more easily. Okay, and we have various reference samples as we explained in the morning. We use that for relative method. So that's about that's about the software stuff, and we can show you on the hands-on session. So later we will do calibration first, and then after that we can show to using this QR code, QR reader to make the life easier, and then we will do a force curve first, and to say how we do the analysis manually, and then we can do a PeakForce tapping. And with the PeakForce tapping, we need to show you the background removal and the sync distance adjustment. Okay, so I think that's it. So today we finished all the elasticity part, and from tomorrow we will starting the viscoelasticity, and we need to consider the modulus and the stiffness is a function of time. We need to use different way to do it, and tomorrow we may go through some part about the force, the strain creep, and the stress relaxation. On Friday we will do the dynamic mechanical analysis, which is DMA. So that's the two techniques to do the viscoelasticity. Okay, that's about our plan. Okay, so today it's the lecture is done, and we can continue to our hands-on session. Thank you.
What time we should meet and where we should meet? We direct meet at the laboratory or wait here? Because tomorrow morning will it be the hands-on?
Yeah. Tomorrow will be also hands-on sessions, because today may not have enough time to finish everything, so we can continue tomorrow. So how about we directly go to the lab tomorrow morning?
Okay.
Yeah.
And tomorrow afternoon is the Booker Symposium.
Yeah.
And you will introduce except the AFM, but also the nano-indentation.
Yeah, nano-indentation
stuff. So it's privilege join, and if possible, also invite the friends join if they're interested for those kind of product. Yeah.
Okay. Thank you.